Hello, welcome to the Honeycomb tutorial and intro video. Honeycomb is a Grasshopper plugin that was developed with researchers at the AWTH in Aachen in Germany, looking to create a parametric method of creating topological interlocking, such as these geometries here. In order to do so, we also implemented the 17 wallpaper groups. If you don't know exactly what these are or are interested in the mathematics behind it, I would recommend doing some research. They're very well documented online. But like generally what they are is it's a set of 17 different translation, rotation, and mirror symmetries that result in different tiling patterns that can tile the plane infinitely. So it takes this base shape called like a fundamental domain, and by applying transformations to it, allow for the geometry to go across the plane infinitely. And so these interlocking geometries, this topological interlocking, takes advantage of that. We'll see a bit later once we dive into the Grasshopper scripts. Here we have, or we can start here. Again, interlocking geometries with a slider just animated in Grasshopper. Done with this script, which is in the example file. We have here 6 different wallpaper groups that each have the same script. And just simply by changing the wallpaper group input, we're able to generate different geometries. That's with this script here, also in the example file. Then we have more interesting behaviors, like this is an emergent behavior from the Voronoi domain component, which again, we'll see. And of course, tilings and output 3D geometry. So to get started, come down here, download the first version of Honeycomb in the example file. Feel free to follow along if you would like. I'm not going to go into detail in this video about the installation of a Grasshopper plugin. This is well documented online. Definitely check that out. So it involves bringing it into the libraries folder and unblocking it and then restarting your Grasshopper. It's not so complicated. You can figure that out. You got that. Okay, so let's jump into Rhino space. So for the majority of this tutorial, we will be working in top view because a lot of the geometry generation is done in the XY plane. And we have here these 10 components that were generated to assist in the creation of different patterns and interlocking geometries, geometric tilings, if you will. And the first, we'll do the wallpaper group component, which is this one. So essentially, all that this is a dropdown that outputs a string. And this string goes into either the get wallpaper group light component or the get wallpaper group component. These are essentially the same component, just one gives you access to more parameters. And so if we try this quickly, just with the light, we have P6 to start. We'll start with this. This component is outputting 4 things: a tree of transformation data, which will be used later for the wallpaper array component. We have fixed points that no matter the fundamental domain, stay static. They're always part of the geometry that you're generating. The base cell, which is sort of this arbitrary diamond that we've chosen. In this case, it contains 6 of the base shapes, 6 of the fundamental domains. And so by taking this and taking the wallpaper array component, this is what I'm calling the very basic workflow. We're able to take this geometry, take the transformation data into the transformation data, and take some geometry. We can use the fundamental domain, which in this case we can see is the diamond, this kite shape here. And this together allows it to tile the plane. If we take something like a point, if we put a point here, oops, excuse me. We can set one point. Let's say this point. So here we have this this base shape, and here we have this point. So if we add this here, now we're also applying this set of transformations, this like generated transformation data based on the wallpaper group. We're applying these transformations to this geometry. So it's repeating them in this six-fold rotation and translation that is resulting in this pattern. The more complicated wallpaper group component has additional settings, more or less. So if we get rid of this, we'll get rid of this, bring this down here. We'll enable this. We can see, let's bring this to P6. It's recommended to try with different things, with different wallpaper groups. But we can see here, this is the same geometry as before. If we give the point again, it's the same as before. We can move this point, changing the patterning, and then also change the different inputs. So here we have the cell dimensions, which is this C. We have the angle. For P6, the angle has no effect, but some different wallpaper groups it has good effect. We have the origin, so where this base point is. And then we have the X and the Y repetition. So if we just increase this for an example, we see we're making our geometry larger or smaller. So it's recommended when you're just starting out to just try this, just try the wallpaper group light component. And as you get more complex, as you understand the way that it's generating the transformations and are able to manipulate geometry in response to the transformations, start using the expert version. So now we're going to move into like warping the domain, a concept that is kind of at the core of the interlocking block geometries. And so here in this example file, where we have like a starting point and we build up from it into different scripts. And then over here we have more complicated scripts, which we'll see in a minute. And then we'll try and do a little bit of freestyling. We'll see how well that goes. So here we have like a warp domain. So we have this fundamental domain. Let's get a curved container out here. We have this fundamental domain, this kite shape. And what this component does, by putting in the transformation data, the fixed points, and the base cell, we're able to pair the edges of this. So this kite shape has 4 edges, and within there's a little bit more of a complicated concept, something that you need a little bit to understand in order to like properly use warp domain and the following things. We have curve pairs that if we apply certain like warpings, or I don't want to use the word transformation because we're using this in a different way, warpings or I guess changes to each of these edges, that they will change between pairs, and if we're pairing them and changing the pairs, it's still allowing this geometry to tile the plane infinitely. So the fundamental domain is remaining a fundamental domain under certain conditions, which this pair edges component is enabling. So here we have 4 edges of this fundamental domain, which means we'll get 2 pairs. And these 2 pairs are obviously the top 2 and the bottom 2. This geometry is quite easy to see. And by adding points, so these points are in the example file, they're internalized, we're able to construct a geometry. This is in Rhino space, not in Grasshopper space. Ooh. What is this? Hello? Try again. Weird. What's going on here? Okay, I don't know what that is. Maybe it's I'm clicking too close to the point. Yeah, I think that's probably it. Yeah. So if we do this, for example, and this point lies on this point, we're able to take this new edge curve, whereas like we have this edge here, we're transforming it into like adding a kink to it. Because these two are paired, we're able to rotate. We're able to rotate this geometry here, and now these two edges replace these edges. And so what warp domain does is it essentially takes this base domain and using those points acts upon it in a way that allows the geometry to continue to tile the plane infinitely. So if we check out this now, we are still in wallpaper group P6, but now we've fundamentally changed the fundamental domain. This was not a good way to put this, but we've warped the fundamental domain, resulting in a new fundamental domain. And because we followed a certain pattern to do it, a pattern that's like that's within this warp domain, this pair domain edges components, it is still able to tile the plane. And so we can see that here with the kite geometry, this is normal. Here with this geometry, now we have this like emergent pattern going out. And so it's very easy, very quick to make different things. And we can come here, we can check this out, and we can take these points and move them. Oops. And move them to parametrically change the entire geometry. And P6 is my personal favorite group, but we can go into P1. And we can do the same thing. So obviously the logic, the translation and rotational mirror symmetries of P1, P6 are different, but the resulting behavior is similar, close to being the same. Cool. So now let's disable this. And this next part, when we make an interlocking block, what we're essentially doing is we're taking the original fundamental domain and we're taking that warped fundamental domain. What's going on here? Oh, we're in P2. Perfect. Okay. P2. So this error we're seeing here, we have, I know this because I created the example file. I knew what the error was. P2, this geometry requires how many pairs? It has three pairs of joints. Here, you can see it's difficult to see this here where it's paired since it's a triangle. But here, when we have the what are these? The fixed points. You can see that this curve is divided here. So this and this are paired, this and this are paired, and this are paired. And because there's three pairs, warp domain requires a minimum of 3 input points in order to generate the geometry. But I'll let you mess with that. Feel free to add, remove points. We'll go to P6 because this is what this script was built for. And here we have, once again, a warp domain and a like the standard suggested kite domain as is predefined by us. And so it takes the interesting part about this these interlocking geometries that we saw earlier here is that both the top shape and the bottom shape are fundamental domains. So here we have the original fundamental domain. Here we have the warped fundamental domain. And so here with these interlocking geometries, we take the fundamental domains, we offset them, and then we triangulate them in such a way that it creates this shape, this thing. So if we take these points, once again, we can move these points. And as we do it, this geometry will change. It will update parametrically. And what's incredible about this is once we put it into wallpaper array, this shape, though it has some thickness, is still tiling the plane infinitely with no intersections, with the edges lying upon one another. So if we imagine this as like a real built thing out of concrete or wood or any material that comes to mind, we can have this shape here, and because of the angles of the neighboring blocks, we're not able to remove that without removing the external geometries first. This is a little bit like sneak peek into the paper content, but check that out when it comes out. So to just recap this, we have the pair domain edges, or pair domain edges component, and we have warp domain. Each of these outputs a different fundamental domain. These two are in 3D space, are offset, and then triangulated to create this interlocking geometry, which is then repeated. Some wallpaper groups, I think P2MM, because it's a group that only contains mirror symmetries, this idea of the interlocking geometries doesn't work. The pairing the edges in the warp domain doesn't work the same way because there are no fixed points and thus no possible warping. So once again, stuff for you to mess around with. So let's disable this. Moving on to Voronoi domain. And so here we have this behavior which came out. This is literally just created with a script. It's very, very straightforward. It's kind of really interesting in my opinion. And so we have the expert get wallpaper group component. And then we have within this base cell, us evaluating that surface with like UV coordinates. So what it does is it takes the base cell, and as we move this around, it puts a point within it, and then based on the transformation data that is being generated from the get wallpaper group component, we're seeing different fundamental domains being created. And we call these Voronoi domains because as you array them, it has the same logic of Voronoi, being that you draw a line between each 2 points, and then you put at the center point, put a perpendicular line that generates the geometry. Once again, Voronoi is super well documented online and in other places, and even in Grasshopper. I think there's Voronoi. Yeah, there's native Voronoi components within the software. And so just by changing this, we're able to see this emergent kaleidoscope behavior. Pretty fascinating, in my opinion. And we can change the wallpaper group. We can go to P3. The logic is the same, just the translation, rotation patterns are different. And if we go into something like a mirror symmetry, we can see there are these lines that stay fixed, but the lines that change are the lines that you're able to warp within the plugin. So that's a little bit about Voronoi domain. We can move on from there. This is essentially taking, maybe before we move on, by changing this, by moving the fundamental domain into a different section, because here we have, P6 again, just because it's easiest to understand, we've been sticking with it this whole time. We have this fundamental domain here, which means the transformation data puts it here, 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 and then moves it elsewhere. But as we move this is now in a different section of the base cell, and so requires updating the transformation data, which is done here. Then this is giving the evaluation point and the new fundamental domain. It's very this one, in my opinion, if we understand up here, this is quite simple. Messing around with it, understanding the different symmetry patterns, definitely going to help you to be more productive with this software. So now we have the component, this top one, get fundamental domain from Rhino, which we can see here. And so this is a component that requires cross Grasshopper Rhino workflow. So once again, we're starting with P6. Again, you can do this with other stuff. We take our base domain. We do a little Voronoi domain because we're interested. And then we pair the edges of that. So if we overlay the cell, the grid points, we see this and this are paired, this and this are paired, and this are paired. So we should have 3 pairs. Yes, exactly. And we take the endpoints and we bake them. So we can do this. So we bake them. Let's just bake them to default. Okay. And now we see here. We have here, here, here. And so what we can do is we can draw curves that lie between, let's connect to a point, that lie between this point and this point. So each pair of edges will have one different, so if we saw before from this geometry, we can see this edge is paired with this edge, this one with this one, and this one with this one. So I'm drawing one curve per pair. We've done that here already. A little bit different. Oh, I chose the same ones. Interesting. A little bit different. but essentially the same. And so we can set this to our curves here. So if we put this into the DIY fundamental domain, now we've created a new fundamental domain. Maybe we want to update this. Wait, what's going on? Oh, of course. Maybe we want to update this so we don't have the self-intersection, something like that. This is a fundamental domain. And by arraying it, we can see the shape going across everything. So this allows you, we're in Grasshopper space a bit restricted to the warp domain that's creating the fundamental domain to be a sort of these rigid edges. See these sharp edges, because like the curvature, parametric curvature is a bit more difficult to implement. Definitely, you're more than welcome to put it in yourself with the native Grasshopper components. But for sake of simplicity in an already slightly complicated plugin, we've kept it to the Rhino to Grasshopper workflow. And so both of these, based on how we've paired them here, we can delete this. Based on how we've created this, now does that. And so each wallpaper group, each fundamental domain and Voronoi domain will have different endpoints. So as soon as we move this, it's going to throw an error because the curves we have are no longer coincident with the edges. So it's important that you're very deliberate with how much you move this, like how much you move the original generating fundamental domain in relation to when you create the output, the Rhino to Grasshopper geometry. Cool. Yeah. You have to, again, make sure that the lines are coincident with the points and that there's exactly one per pair. It will throw an error or have some weird behavior otherwise. So now we have another interlocking block. So the lofted interlocking block rather than the triangulated interlocking block, which is using essentially the same logic as the other one. Oh, and we have a little grasshopper hang. So Voronoi domain, we're going to pair the edges. This is the same. I believe this is precisely the same. Yeah, P6 at 0.42 with 0.52. And then we'll create this geometry. And using the same logic as we were up here with this interlocking geometry, we have the beginning, what is this called? We have the beginning fundamental domain, excuse me, the beginning fundamental domain, and we have the new Rhino generated fundamental domain. And we can use the same logic, the offset, and in this case, just lofting it with a Rhino space loft command, to then create a more wiggly interlocking geometry. So yeah, these are the basics of the components of the plugin. The 10 components we've gone through from Rhino, we've gone through Voronoi domain, both of the wallpaper groups, both interlocking blocks, the pair domain edges, the wallpaper array, group selector, and the warp domain. Cool. Great. So now let's check out this next section. That these two are the generating scripts here. So this script, this top one, or this bottom one, is responsible for this animated interlocking geometries, and this other one is responsible for this like almost string art generative stuff. So let's check out the top one first, the string art, line patterning, as I termed it. So here we have we can start with P6, but this one's really fun because just by simply changing the wallpaper group that we're working within, we have like different behaviors. Let me take a sip of water. Got this giant Nalgene. Go hiking. All right, thank you. Yes, so we have the get wallpaper group. We have the Voronoi domain, we have the pair domain edges, and then from here we sort of freestyle a little bit with the native Grasshopper components. So first we're dividing the curve. into like many points, and then we use this component called offset, tree offset, relative item, which has an input called tree offset. Yeah. We have a tree, we have an offset, and so this offset is essentially, I'm not going to go into too much detail of this. This is a Python component, which is basically just creating, like, it's string formatting essentially. So we have the strings, the tree offset, a little more string, the item offset, and which allows us to just change this to update the string rather than typing this out every time. Relative item, I'm not going to explain this component, but it takes, okay, I'll try and briefly explain the component. It takes a tree and then kind of maps it out in it like kind of puts it in like a dimensional space, and then depending on the offset, you step between along branches, along items, depending on which two items you want to pair. So for example, 0, 0 will get paired with tree branch 2, item 3. And as you offset, as you continue stepping through, it will continue offsetting by like the same amount. Look into this. This is also like a native Grasshopper component, so check that out online if you would like. So just by simply doing this, we're taking these points, pairing them together in some way as defined by the tree offset and the tree structure, and then we're drawing lines between them, which creates this like really fun, interesting like string art, which we can then put into curve geometry and take this transformation data and wallpaper array, and instantly we have this this like string art that's created from just this simple script. And what's crazy is if we move the Voronoi domain, it's a little bit slow because of all the curves it's generating on my computer. We're able to change the art. If we change the wallpaper group, it's the same. We have this P4 pattern, changing the Voronoi domain. P3, or we were just in P3. No, we were in P6. It's like similar. And so we can then come down here, change the tree offset to 1. Change this up a little bit, and you can see how quickly and easily we were able to generate these 6 different patterns in the Food for Rhino documentation. So this is essentially this component. This is a custom preview if you're unfamiliar. This is also it just allows you to look at a geometry with a certain color rather than the red and the green that we've been looking at before. So pretty straightforward. Then we have over here the interlocking block geometry. So if we come here just to check it out, we're doing our make interlocking block like foundational script here with predefined edges, with a warp domain, with an interlocking the make interlocking block with a wallpaper array, and then we have a center point that's generated. Is it here? No, this is making the center point. So we have. Also, check this out. We'd mass sum the x and the y to create the center point of all of these center points. And then we're essentially just moving in and out each geometry based on a vector that we generate from the center point to the center of the block. So as we move this, it moves out. As we move this, it moves in. And check that out in 3D space, maybe a bit better. And so we can see here like the interlocking nature of these geometries. Just to recap, I know I went over it super quickly with this one. We're making the blocks, and then we're taking each centroid of it, averaging the centroids into a center point, which is here, then constructing a vectors between the center point and each centroid of the volume, and then multiplying that vector by our between 0 and 1, to create the animation. And then we have another custom preview, this time with blue. So yeah, pretty straightforward. There's a few other things that I want to briefly show you before we'll wrap this up. Firstly, everything that we're working on in the plugin has to do with the XY plane. If you've noticed, like we were working in top view, and even the interlocking geometry stuff is in the bottom view. So there's a few things. So first, let's go here. Let's copy this, bring it over here as a new example. Let's disable this quickly. I'll enable this one. Okay, so we have this this fundamental domain that's being tiled a bunch based on the grid cell. This was the first example, you got it. And so we can also take, let's make a cylinder. Let's put it in the fundamental domain somewhere. And then let's make geometry, set one geometry to this guy. And based on our pattern, we're able to not just manipulate 2D things, but also 3D, which we've seen already with the interlocking geometries, but it can be any geometry you would like. It doesn't have to be generated via the Grasshopper plugin. It can be some shape that you like, that you enjoy. It can be some like Zaha Hadid-esque curvy linear thing. It can be something that like warps between each fundamental domain to create this like wavy patterning. Like you're creative, you got it, you know. So this is one thing, and then the other thing, well, there's two more things. One thing is less complicated though. If we take orient, this component, and we take XY, because this is the origin here, it's 0, 0 at the XY plane, right? And this gives 0, 0 XY plane. And we'll do YZ. These are also native Grasshopper components, but we can see quickly, well, the planes are huge. So XY is, hit F7 to get rid of it. XY is this plane with the x-axis and the y-axis. YZ is this plane with the x-axis and the y-axis. So if we orient this geometry from the XY plane where we started to the YZ plane, what we can see is now we've taken the geometry and we've put it on an end. So if you're working on something and you want it to go up like vertically, whether it's in the side of like let's say it's an architecture project with a facade that you've wanted to pattern, we have this potential to just quickly use the orient component native to Grasshopper to do that. Cool. And we'll do one more thing. So we're going to make a script that uses an attractor here. So let's build it from the ground up. So we'll start with the wallpaper group selector. And let's use the light version because I'm not interested at the moment in affecting those other parameters. And so with this, what we're going to do is we are going to, let's warp the domain, which means we need to pair the domain edges, which takes each of these here. So now we have this paired domain edges. Let's not work in P6. Let's work in a different one. Let's work in, about P2. Because we were looking at this earlier, right? So we have I, we have T, and then I think, how many pairs do we have? We have 3 pairs, which means we need 3 points. We'll go 1, 2, 3, and then we will point. And we'll bring this in here. We'll check this out. It's a bit of a mess. This requires some tweaking. That looks good. This looks okay. And then let's see here. Okay, and then quickly let's check out what it looks like when we array this. So we have the geometry, we have the transformation data. This transformation data is a curve pair transformation, not the overarching we want here coming in here. And so this will create this cool like lightning lightning bolt effect. Not intentional, but emergent and fun. And so what we can do now is we can have another point. Let's just put it here. We'll call this one our attractor point. Oop. Excuse me. Perfect. And so now we'll just do a quick scale thing. So we'll do scale. We'll scale this geometry from, and we want a center of each geometry. So the center right now is the 0, 0 point. Let's use area, the area component, to get the center of this geometry. Oh, we need to, so each of these are 6 different curves, so we'll need to join them first. So we'll join curves. Now we can get the center. Now we have the center of each of the geometries, which happens to be here at the end of that point. And so this will now act as our centroid. And now we have this point, we have our centroids. Let's set up a distance between 2 points. So we have distance between centroid and our attractor point. So this is now giving many values. I have the feeling that maybe we should also flatten this. Can we flatten it here? Yes, we can flatten this here. And we'll put this in here. So now, right now, we're just scaling these interlocking geometries, but we want to scale them parametrically based on the distance to the attractor point. So now we have a list of distances, and we'll set up bounds to create a domain, and we'll set up a remap. And so remap takes a set of values, which are our distances, a source domain, which is like the max and the min of the source, and the target domain, which we can construct domain. So this by default is 0 to 1, and then we can remap this to here. So now as we move this geometry, it scales them based on that. So what we can also do is we can take, what is this? Cannot scale with factor 0. Okay, so to get rid of that error, we could do where it says 0, have like 0.0001 or something. Now we're not scaling with 0, we're scaling with a very small number, so it's not invisible, but just very, very tiny. And so very quickly we're able to do this, where the geometries are scaling based on that. We're able to also create a maximum. Let's say we want these up here to be scaled such that they tile the plane properly. So we want a maximum or a minimum. We want a, oh, this is time. This is not either. So we want a minimum. So we want to take the minimum value that is given between the domain 1 or 0.001 and 1.5. So now when we do this, now we're overscaling. So some of these remapped values are above 1 and self-intersecting. So we can take this and then we can choose between this value and 1 to then set the maximum scale factor at 1. So now as we move this up, we're able to keep these like small and keep these interlocking based on like the range that we've set up. This script, this logic here, if you're new to Grasshopper or not an experienced Grasshopper user, is something that's extremely important for like parametric generations of things. Taking some parameter, taking the boundary, like the bounds of them, finding the max and the min, creating a domain from it, remapping that domain to a different domain, and then creating some output geometry based on it is very important in my opinion. And so I would review this and fully understand what's going on. I'm not going to go into it because this is, again, a tutorial about the Honeycomb component, not Grasshopper in general. So if we take, just to take this one step further, we can take these and we can create a interlocking block triangulation from this. So we have the initial set of curves here. We have the amended set of curves. We have an option for the offset. We'll keep it at 1. and we have cap, whether or not we want the top and the bottom geometry. So we can do false or toggle to switch between false and true. We can see if it is false, then this geometry here has only the sides, not the top. So if you remember this 3D geometry that we were looking at before, this geometry was generated using this interlocking block logic, but getting rid of the top and adding a thickness to these walls and then 3D printing it. So here we can see this Voronoi domain, or not it is a Voronoi domain, this fundamental Voronoi domain on the bottom, and then the warped domain on the top. And by adding a thickness to the wall and 3D printing it, we were able to create this like quick snowflake effect, which, yeah. So we'll set it to true for now, such that we have our interlocking geometry. Let's make it a bit bigger. Let's say the offset is 3, just so it's a bit like, there's a bit more chunk to it, you know? And then we'll take this offset, we'll put this in here. We're gonna have an issue here though, because we set this script up for curves, but what we can do is we can use volume. We can do this. We can replace the centroid here and this here. We can flatten this to keep the logic the same as flattening this. We can get rid of this and we can put the geometry in here. So now when we're scaling this, rather than scaling this like these 2D geometries, we're now scaling the 3D geometries. So over here, they're interlocking, and as you get closer to the attractor point, they shrink and the space between them increases. So as you can see, it's pretty flexible, and the geometries are quite flexible and able to be manipulated further with the native components within Grasshopper. I apologize if I went a little bit quick. Definitely slow down the video, pause it if you need, follow along if you would like to as well. But hopefully this was informative and helpful, and you learned a thing or two, both about wallpaper groups, interlocking geometries, and how to use the Honeycomb Grasshopper plugin. There is a support email if you have any questions or concerns or find any bugs in it, or if you just create something really interesting that you'd like to share with us. Anyways, thanks for watching. Hope you enjoyed. Please have a good day.